So with that, let's get started with Ralph, and we're back on track here. I forgot to, so Ralph is our latest resource expert to come in for us, and you are on camera to your left. Don't worry about that one. That's underneath there, so the other side would be better. Okay. Oh, and just so you know, they are welcome to interrupt you as you go along.
Oh, no problem. Sounds like my class. So some of you will have seen some of this before at NGA East, held about a month and a half ago. But I wanted to talk about the simulation and validation study that is going on in the NGA East, and also bring into an idea basically of what might be taking place with regard to the West. In other words, possible other sources that should in fact be validated. So this is a program, as many of you may know, that is sponsored by PEER, or it's run through PEER at least, but it's sponsored by the U.S. Nuclear Regulatory Commission, and with a lot of work coming in from the U.S. Geological Survey as well, and others. Now, in the finite fault simulation group in the East, working on the East, there are a number of different groups. The ones that are listed here are actively participating right now in the validation studies. It's ongoing, and I'll come back in a moment and explain, what is taking place and how we're trying to do this. Now, one of the things about the validation that we had to determine first was basically which earthquakes were we going to use, okay? And what type of earthquakes. In other words, the selection of earthquakes should in fact reflect basically the type of earthquakes that occur in the East. So this is a figure taken from the World Stress Map project, where they're mapping stresses, a lot of this stuff. And we're interested in this region, of course, that is to the east of the Rocky Mountains. And these are indications of stress directions. And it's not a very good map from my perspective, in the sense that it's hard to interpret. For a seismologist, the balloons are a lot easier to interpret, okay? Because when you see balloons that are like this one here, where you have, the big blue or it's solid in the middle, you're looking at reverse faulting earthquakes, okay? If you look at something that looks like over in here, where you've got this sort of, 4 quadrants, then you're looking at strike slip. And the red ones in here, it's nice, they're color-coded in the sense that if it's white in the middle, then they're normal earthquakes, normal faulting events. And what we see is that basically in the northeastern part of the US and also eastern Canada, to a large degree, what we see are reverse faulting earthquakes. In other words, like this, and coming down, I'll talk about the one in Mineral, Virginia, also a reverse faulting earthquake. However, if you come further towards the Midwest in this, you start to pick up earthquakes that have a much more strike-slip component. So you're going from a regime basically that would indicate compressive stress into a regime that has strike-slip, or you're moving towards the extensional side, but you haven't made it there until you come way over here into the Intermountain West, where you start to see a preference for normal faulting events, indicating that this is a region that is undergoing extension. And so the choice of earthquakes really was based on this idea that we would be looking at earthquakes which would represent what would happen in the, let's say, Middle America and northeastern the United States into Canada. And so what we're looking at when we started to look at these earthquakes, what we were looking at were earthquakes that were reverse faulting or strike slip. And I should point out that at the time we made this decision, the largest earthquake in the East for which we had data was a Saguenay earthquake of 1988, a magnitude 5.8. And then, as luck would have it, the Earth provided another example that we could use, which was Mineral, Virginia. Okay, this is a magnitude 5.8 earthquake. What I'm showing over here, the most important one I think is in figures here, is down in here where we're looking at the aftershocks at depth. And you can see a fairly steeply dipping fault plane The dip is given right now at about 46 degrees. It's a reverse faulting earthquake. It's a very interesting earthquake, and I'll tell you why, because it'll come back and it'll affect our later decisions as well. So far as we can tell right now, this earthquake has anywhere, the estimates coming in are around 300 bar stress drops. You'll hear higher numbers than that, but when you have to ask that person specifically, okay, if you got a higher number than 300 bars, that's a Brune stress drop. Did you use a different relationship? Did you use Madariaga? Did you use Sato Hirasawa? Did you use the work of Snoke? Did you use the work of Silver? You need to know who calculated, what is the relationship between corner frequency and radius when they go to calculate that stress drop. Brune stress drop is somewhere now on the order of 300 to 400 bars, and basically at the depth of this earthquake, it's about half of what is the available stress. So it's an interesting event, as are the other ones that we had chosen initially. Initially, we had chosen Riviere du Loup. It's a small, I'll point out some of this in just a moment, that it's a small event, relatively small, 4.6. Basically looking like a point source. It has some close-in stations. I'll show the station distribution in a moment. And the really good thing about it is that it represents a typical earthquake, northeastern United States. It has a pretty good distribution of stations, and they're all modern stations. So we've got horizontals as well as verticals. And so this was it's a good event. It's a good reverse faulting event. Saguenay, as many of you in this room have worked on it before in the past, you know that this is how do I put it? It's a complicated event. It's extremely deep, okay, relative to most, in the sense that basically the hypocenter is at about 26 kilometers depth. The Moho is quite deep in this region, deeper than most of the US, where it's down to basically something on the order of about 44 kilometers, so it's still well within the crust. But it's a very complicated event, very hard to model, and not a lot of good data, the closest station being something on the order of 50 kilometers. So, when you look at what you have to work with for earthquakes, you'd really like earthquakes that you could use in the eastern United States, but in fact, you don't have very many. Now with Mineral, Virginia, at least we got another one. And so we had to go looking elsewhere where we might find other earthquakes that might represent somewhat stable continental interior, if not stable, or continental interior, at least somewhat stable. And then we just had to look for earthquakes which had some representation for the stress field that we expect to see in the east and in the eastern United States, central and eastern United States. And so we chose, one of the very first ones was Totori. Totori had not been used in the NGA relationships in the West. It's an excellent earthquake, magnitude roughly 6.7. It has tremendous coverage thanks to KICnet and KNet. I'll come back to it and describe this a little bit more detail, but it's in a region of Japan, in fact, which is not known for having a lot of earthquakes. So it is interesting because Totori is also an interesting case of a blind strike-slip earthquake, in the sense that it has very, very large slip near the surface, but it doesn't break the surface. And so it's a very interesting earthquake to use. Northridge, the next one on the list was an obvious one. In other words, it's a blind thrust. It has very good coverage. It's bigger. It's an earthquake the same size as Totori, and so it's comparable. In other words, we're looking at a blind strike slip. We don't have a lot of evidence that earthquakes in the east have broken to the surface, so having them blind is really representative of what you might expect. And so we're looking at Northridge and Totori to be, they're complementary. One strike slip and blind, the other one is thrust and blind, or reverse. Loma Prieta was chosen because it's a bilateral rupture, and it has a combination of both. It's an oblique faulting because it has a combination both of strike slip and reverse faulting in it. And again, an earthquake that is basically blind. It has some offset, but most of it's due to shaking. So another good earthquake. Imperial Valley is probably somewhat of an outlier in the sense that here you have a strike-slip earthquake in sedimentary basin. It's excellent for the west, but it's it's just got very good coverage, and we thought, well, if you wanted large side effects, this would be one with it. Probably not the best, always the best choice. Chi-Chi we chose because it's the largest event for which we have a lot of data. There is another earthquake, a magnitude 7.8 earthquake, the Wenchuan earthquake, that might be appropriate, but in fact, getting the strong motion data from China, where they will, it's not getting the data, they will give you the data, but you're not allowed to, in fact, place the seismometers or the accelerometers to any more accuracy than 1/10 of a degree, which means 10 kilometers. So that's not very good when you're talking about trying to get in close. It has good data, but it's hard to use. So these were the earthquakes we chose. One of the things about it is that, you know, in doing this, you have to specify, one of the most important parameters that we have to specify is basically what is the size of the fault, what is its geometry. And this has to be given for each earthquake. That is the bare minimum so that everybody is in fact working with at least the same maximum size fault plane. And then from there, they can play with it. And we also have to give a hypocenter because the hypocenter is a fundamental constant in affecting the ground motion. So we're left with that. And then we move on to the idea of that, okay, you put this geometrical plane into the medium, the question becomes, fine, you did that, but what type of medium is it? And so you have to then provide some idea of what is the velocity structure in the area in which you are doing the simulation. This is an example for Saguenay. It shows what the distribution is, what the Q structure is, what the velocity structure is, what the density is, okay? And this is something that everybody will be using, okay? Now, everybody up to a point at which we'll get into it, but we still haven't decided basically what to do about the side effect itself. This is really the path effect. And so we're, you know, this idea over here where we're sort of looking at VS30 from Walden Allen, as was pointed out in the meeting that we had with on NGA East, this is probably not a good proxy for stations that are in the eastern US or in Canada. The shear wave velocities are a lot closer to on the order of about 1,500 to 2,000 meters per second. But we do give all the stations what their latitude and longitude is that they'll be working with, and then they can use this. If you go to a place like Totori, you can get lots and lots of stations. In other words, this is only a partial list of all the stations that we're dealing with. And the VS30 is taken from Pier, but there are measured values for the KICnet and KNet stations. They're not always down to 30 meters, but there is some measure of VS30 in all of the Japanese data for KICnet and KNet. And so we can give then something like Totori. And so when you get something, you give an earthquake like this, a strike slip earthquake, you show where its epicenter will be and specify the depth of the hypocenter. We start with an initial model of what the slip distribution might look like. Notice this does not go all the way to the surface. This is at 1 kilometer depth in here. And so there's large slip near the surface, not so much in here. We chose a particular model that was taken by Pietanesi and others. But people don't have to use this model. It gives an idea of the type of slip distribution that people have derived from inversion. But it does show in the upper figure here, we are showing all the stations that are part of the validation. And so everybody must, in fact, provide some method of validation against all these stations. And again, in the validation, the primary validation is going to be the response spectra. We're going to be looking at standard deviation and bias as a function of period. Of course, to get to that point, what we're really doing first, though, is, in fact, we're computing synthetics. In other words, we're computing synthetics from kinematic models in which what we're going to do is we're going to take care of calculate the ground motion, We'll use this ground motion then to calculate the response, and then from there we will go forward and calculate some estimate of what our bias and the confidence levels are on the bias, as well as the standard deviation. An example of this is the previous synthetics were taken from a calculation at UCSB. This is a compilation of the fault parallel and fault normal bias. This was done by URS simulation group. It's headed by Paul over here, but Lawless was the person doing it. But it's a method that has been developed at URS. It's a method that comes from work of Arvind Patarka and others at Kyoto at DPRI, and then later improved upon by Rob Graves, and has continued to evolve, okay? And the idea is that what we're trying to do then is looking at the response spectrum. We're comparing the observation divided by the simulation, and the idea is to look at this as a function of period. Now in this case, the black line over here indicates the limit. So this is very, very short periods. This is long periods. And this one is stopped at about 3 1/3 seconds. So it's in this range that we're looking at. But this is a typical type of function that we're looking at. But again, what we've added are a few other conditions on the bias. For example, this is the standard approach. The green line, the green band, I should point out, is the standard deviation. And the yellow bar in here is the 90% confidence on the mean. That's why it's smaller. And you can see that it's period dependent right now. But when you average lots of these, as URS showed in its presentation about a month and a half ago, over many, many different earthquakes, the bias is very, very stable and near zero. But on the other hand, bias is one of these items that when you're averaging the bias in this way, you realize that you are in fact taking many different stations for that given period. And those stations are at different distances and different positions with respect to the fault. And so one of the things we wanted to look at was to say, well, because we'd like to say, well, is bias a function of distance? Because you could imagine that you could get zero bias by overestimating the amplitudes in close, underestimating those far away. When you average them again, you get zero bias. So the idea is that just as the developers work on looking at residuals as a function of period or looking at it as a function of distance, we're looking in our own simulations, bias as a function of distance. And this is one such example at 1 second period. Another aspect that we're looking at, of course, is that we're not trying to match any particular empirical curve, but we do want to see what PGV looks like as a function of distance. And this will become very important later on when we start to look into Canada. And there are some unusual, not unusual, but let's say surprising attenuation with distance factors that are used. But we'd like to make sure that we're capturing that we compare, when we compare against the data, what is observed and what is synthetic. This is an example from a UCSB simulation for Totori, and the black dots here are the observed, and synthetics, you can imagine that these two go together, these two go together. You know, they're always at the same distance, but the general trend is the same, even if in fact you don't see the dots lying this close together on any given one. So it's one of these things we're trying to look at. Well, the different earthquakes are interesting. I'm only going to hit a couple of them because they're the ones in the east. This is a good record because we have a close station in here that is only about 15 kilometers away hypocentrally, and absolutely bizarre. Okay, it's the predicted amplitudes are completely larger than what you would expect. And it's a very unusual amplitude in here. It looks like somehow it lost a lot of energy. You can predict these out in here a lot better. But it's again, this is basically a point source, a thrust, so it's not too hard. When you come to Saguenay, now what happens is that your stations tend to be much farther away. The closest station is up in here. It's about 45 kilometers away. You've got another one over here, maybe 60. Most of your stations are at fairly large distances, 100 kilometers or more. And they make it very, it becomes basically almost a point source. But it's, of course, got azimuthal distribution because of the radiation pattern. So those were the earthquakes we had. I'm going to end here because I'm running out of time and we want some discussion. So earthquakes, potential simulation earthquakes for the western U.S. So the ones I would add are Parkfield, okay? Hector Mine, a magnitude 7. Kobe, a magnitude 6.9. The others are the same, except for that last one down in here, which is Tohoku. Now, why these? Well, when you look at Parkfield, it's only a magnitude 6, but it's got a very high station density. There are large variations in the peak amplitudes. There are large, and the accelerations are large for a small earthquake. You look at Hector Mine, it's complicated by multiple faults. It really has a geometry that's extremely similar to what you see in the Hosgri and the shoreline fault. And it's got that complicated rupture, in fact, where one branch ruptures, the other one doesn't, and then it does rupture. And so it's a very good analog if you were to look for something with the Hosgri and the shoreline. The Kobe earthquake is relevant to something like a Hayward rupture, you know, and it's very interesting because of the fact that you've got mountains, you have the possibility of these additional additional path effects that come into play. And Tohoku obviously is an analog, you know, for Cascadia rupture. It may not be relevant to Diablo Canyon, but on the other hand, it is extremely relevant, let's say, if you were looking for ground motion and you were trying to make ground motion predictions in the Pacific Northwest. And I see I duplicated that at the bottom. The other ones are the ones we've already used, but I would keep them, okay? I mean, if you look at Chi-Chi, it's an obvious analog. If you look at the Sierra Madre Cucamonga rupture, it's the same length, the same type of thrust. It looks exactly like what would happen if we had a 7.6 on the Sierra Madre Cucamonga, which is what the predicted magnitude is for such an earthquake. The Imperial Valley is one that you keep because basically you do have ground motion in a deep sedimentary basin. And so these are the type of things why you might keep the same simulations, but there are a few others that should be added probably to the list. And with that, I'm going to stop.
But back to your list. So this is part of where we're starting our discussion. Hector Mine, while sounding nice from a source point of view, does not have many close-in recordings, right? There
True.
is one.
There's one. That's the real weakness of something like a Hector Mine event. You just don't have, even if you took something like Landers, which is much bigger, you again, except for the one close record at Lucerne Valley, the next one is at Amboy, and that's about 30 kilometers away. And so you get very quickly away from the fault. That's why, I mean, Parkfield is too small, but it's got lots of data.
It's not too small, and so yesterday we were talking about what matters, and for Diablo Canyon case, close into a moderate-sized earthquake, so 6 to 6.5, is really important. And so, you know, our shoreline fault, this is kind of the size it will make. It may be a little bit bigger, but this is the right distances. So I think that one makes a lot of sense to bring in.
Parkfield makes a lot of sense, and then I would throw in, you know, if we're looking, let's suppose as this subject matter here is Diablo Canyon, I would say that the two that I'd be looking at really closely, I'd be looking at Parkfield, and I would be looking at Totori. In other words, what happens if you have most of your fault rupture? I mean, there is, you know, papers by our good friend right behind you, Paul Somerville, and others and there are some of this in the NGA relations, about the idea whether or not buried faults, in fact, have a greater ground motion potential. You know, I mean, where the surface, it doesn't break the surface. Totori is exactly that type of earthquake. And so in the sense of really, you know, understanding what might be ground motion from an earthquake like that, Totori and then Parkfield.
What's Totori look like for hanging wall sites, Jennifer? Was there much there?
It's strike slip.
Oh, I'm sorry.
It's vertical.
Oh, it's vertical.
So it's got lots of hanging wall both sides.
Okay. Sorry.
Yeah, it's a vertical fault.
So we do need to try to find some thrust. We've got Northridge.
The other possibility, if you want one with a good earthquake that broke the surface with good hanging wall features, is the Chuetsu-Iwate earthquake of 2008 or 8 or 9. It's 2008, I think. It's called the Chuetsu. It's called not Chuetsu. Miyagi-Iwate. The Miyagi-Iwate earthquake. This is the one with the trampoline effect, where you had the 4G, the very famous one. But forget that particular spalling event, and look around at the rest of it. It has some interesting records because it's got some records in the valley that are about 2G, and it has many stations which are on the hanging wall side. And it did break the surface. It didn't break the full length of what they think the rupture length is, but there's definitely offsets of meters, you know, for a short period of the fault length.
Have you looked at that event, Paul?
I just looked, yeah. But I would add to that, you know, the handful of events that occurred out near the Niigata area between 2000 and 2010. I think those are all thrust. Some of them have a bit of surface rupture, I think.
The 2004 set is really good. Because the reason for the 2004 being a very good set of the Chuetsu earthquakes is that the 2004 series, you have the main event, which is a 6.8, but it has 4 other magnitudes greater than 6 in the aftershock sequence recorded at the same sites. So if you want the inter-event variability, that's a very good set of earthquakes to use. Because now, it turns out that those earthquakes are not on the same fault plane. It's one of these conjugate systems, and so you get the main fault. You get 2 of them, I think, are on the same fault plane as the main one, and then the other 2 are on the conjugate fault. But they're all in the same region, so they wouldn't necessarily have the same hanging wall, but there'd be a lot of hanging wall effects. In other words, but at the same time, it's a very good. It's very well recorded. It has. And it has some very large accelerations. I could dig it out of my, somewhere out of my.
We need a good, the right source, you know, a good station distribution, and then site conditions for the stations.
And these are all recorded on KNet and KickNet, so you've got site conditions completely taken care of by the Japanese.
Okay, any other suggestions or validation events? So right now, I would say Hector Mine just isn't going to do it for us because we're too far away.
Right.
Tohoku, for us, that's not of interest. So,
But Bob says it's really.
no, it's great. Do any of you think it's valid?
For ingest subduction.
Only if you're dealing with subduction.
Would we include a Tohoku event?
No, it's not for Haas. I mean, it's not for something here.
Okay.
No.
If your simulation works really well for this, it doesn't tell us that it will work really well for us. Although
Right.
it might, you feel better if you had a method that worked
All the way
over
around.
such a broad range.
Yeah.
What else? Any other events come to mind? Paul, you thought of any that you think would be good validation events?
Other than what I just said, no.
Do you think the data on the 2007, you know, that, I mean, there's a lot of good data on that, but most of the data, I guess you'd have to say, is in fact, most of the data inland is on the hanging wall side. It's not over the fault, though. I don't think that the fault extends far enough. I don't think it breaks, let's say, the depth of the fault, the deepest part of the fault is basically just outside the coast. So it's not coming underneath. In other words, you're on the back side of the hanging wall. In other words, so technically you're not really over the top of the hanging wall that you would expect where you want your stations, but all those stations at the power plant and this and that and anything on the land is basically back away from the back edge of the hanging wall.
Okay, Walt, are there, you guys have done a lot of validations. Are there events that you have validated against that you think are given a good constraint that you would recommend?
I agree with Paul. I think Nagata is probably the closest analog. Roughly the right magnitude. It's a thrust event. There's good station coverage.
Is that the 2004 or the 2007? Because there are two of them.
The larger one, I think it's,
Okay, that's the 2007.
yeah,
I think it's a, I don't know, is it much
There's
bigger?
more than just those two. There's-
Pardon?
yeah.
There's more than just those two there. I don't have a list, but I'll look for one.
Well, but the 2007 is I think like 6.8.
Kashiwazaki?
Yeah, and the 2004 is a 6.8 or 6.7. But it's farther, it's about, I don't know, 70 kilometers to the north of that one. And
But in addition to the specific Dial Canyon geometry, any other ones that you have used that are, let's say, good for just checking the simulation? Because that's part of what we're trying to get at, that there was enough, we thought it would make good station coverage and so forth, and site conditions available that's not in this list.
oh, the other one would be Lochwillow. Lochwillow has, it has two, maybe you could, depending on where you want to put the northern end of the fault, Lochwillow has at least two stations sitting right above the hanging wall. And then it has those four stations slightly to the north that are right at the edge of it. In other words, they probably aren't on the, they're not on the hanging wall, but they're right at the northern edge of if it's dipping like this, they're sitting up here. But you have two stations that are really close to each other in the city of Lochwillow. They're two different stations, are sitting right above the hanging wall.
But it's normal fault.
It's a normal fault, though.
Just looking at the NJ flat file, looks like we have about 5 stations that are actually on the surface projection of the fault plane.
Of Lochwillow?
Yes. And then we have one just on the footwall, and then just a little bit further back from that.
Yeah, normal faulting of earthquake,
Yes.
though. Yeah, that's,
Correct.
Would it be interesting to consider the Chi-Chi aftershocks or any of the Taiwan events?
The aftershocks are up in the mountains, and there might be other, like Chi-Chi aftershocks, as I recall.
they're all much deeper. In other words, the Chi-Chi aftershocks are on the, if you look at Chi-Chi aftershocks, all those big sixes, they're at the deepest part of the fault. In other words, so they're down at the bottom of the base of the Chi-Chi main shock, and that's why they look like they're in the mountains, because they're way back in the backside. So they're in the deepest part. They're much deeper than let's say, none of the shallow aftershocks were that big.
But there may be some other sets we can
Some other
start to
crustal
look at,
events,
yeah.
right. Because you have the VS-30s for the stations, hopefully.
It would need to be something with close-in data
Yeah.
to really make it work.
Yeah.
Other thoughts on the validation? You had said Christchurch, Yusef, right?
Oh, yeah. Christchurch, the Darfield earthquake, the magnitude 7 has got really good directivity headed right towards the city of Christchurch. The February 22nd earthquake, the magnitude 6 that caused so much damage, there's one station that is sitting on the hanging wall, above it, and the rest of them are on the foot wall, but there's and because the plane is sort of projecting into the city. So most of the city is sitting on the foot wall.
We do have issues there of some pretty severe site conditions and
Yeah.
soil failure that most of these kinematic models are not equipped to take on. So I don't know if that's going to make that too difficult to use for this case.
I think the site conditions there must be horrendous. Given how much liquefaction took place. There's one or two stations that they describe as being on rock, and then the rest of them look like they're on the soil that huge fractions of it liquefied.
And so is there a reason we don't bring along Coachella, for example?
Coachella has, it doesn't have that many records. When people look at inverting the strong motion records, they invert 5. The closest one, the one that basically gives indication of super shear, is the closest one to the fault, but one of the channels is gone. So I think it's the fault normal, in fact, is gone. It doesn't have that many stations actually that are close to the fault. Duce might have more. In other words, the earthquake that occurred in November of 1999, that probably has a few more. I know that there are 3 or 4 stations that Michel Bouchon had put straight on the fault within just a couple of kilometers. It's now in the, I think he's got it now in Cosmos database and also in the National Center for Engineering Strong Motion Data. I think that those stations are now available, the records from the 5 stations that he had. And then there are about 2 others that are in, there's one in Duce and then there's one nearby.
Bob, do we have those are those in the NGA file?
Are they the Lamont stations?
Pardon? They're not Lamont, no. These are not Lamont. These are stations that were put in by Michel Bouchon. And
I don't think so.
Yeah, that's, so I
Yeah.
think
these
to
are
our
Leonard.
list we need to put on to bring those in if there's some close-in ones. You said you think they're in Cosmos.
Pardon?
You think they're on the Cosmos server then, if we just.
I think they might be on Cosmos. I'll have to take a look. I know I can get the data because Michel, you know, he's a good friend of mine, and but he showed them to me one time. They're really incredible because he has like 4 or 5 stations right across the fault. The reason that they're there is because it was 8 o'clock or 9 o'clock at night when he was putting them in, and he got tired, and they just put him on the fault. The next morning, the earthquake occurred.
Wow.